Next up, I think I'm going to get this right, so please forgive me. Kayode Olumoyin. Excellent. Okay.
Hello, everyone. I'm Kayode Olumoyin. So in this talk, I will be talking about a predictive tool that may help clinicians to stratify the eligibility of bladder cancer patients for an immune-based therapy using patient bladder tumor data. So the immune-based therapy I'll be talking about is the adoptive cell therapy with tumor infiltrating lymphocytes. So our collaborators, Tumors et al. In 2012 and others, they've been able to show that ACT with TIL show promise for patients with metastatic melanoma. And in another study, our collaborators also show that the feasibility of tumor infiltrating lymphocyte expansion for bladder tumor to be around 70% effective. So, but first, ACT with TIL, there are 3 phases in this immune-based therapy. In phase 1, the primary tumor is going to be resected. It's going to be minced into small fragments, and it's going to be plated in media. And then after 4 weeks, the expanded TIL is going to be measured, and the remaining tumor material is going to be mechanically and enzymatically digested. Phase 2, there's going to be a flow cytometric analysis of TIL from each of the fragments that, and then the reactive T cells are going to be collected. And then in the third phase, the TILs are going to be expanded using a rapid expansion protocol for a period of 1 week. And this expanded TIL is going to be infused into patients. And in bladder cancer, this is going to be done intravesically. Towards the end of the talk, I'm going to mention a clinical trial that recently opened at Moffitt, for this immune-based therapy. So the goal of my project is phase 1 of this therapy, which is really to develop a quantitative predictor to determine whether tumor, given some features about the patient, about the tumor, will be able to produce functional T cells. And the motivation for this is that, well, for bladder cancer patients, time is expensive. So knowing early patients for which this therapy, for which a TIL cannot grow, it will be important for them to find an alternative treatment. So the available data for this study was taken from our collaborators, Park et al. 2018 and Aiden et al. 2021. So this data has 56 patient data. So some patient data that have been contaminated, those ones were removed, and there were over 100 features to start with, but we did remove some of them that were like an identical copy or a combination of some other features. So we have 67 features, which being subcategorized into demographic features, right? So those are just like the surgeon, those who performed the resection, the sex of the patient, age at surgery, race, ethnicity, BMI, surgery, and whether they are smokers or no. And there were 34 clinical features. So these are the tumor grade, the stage, histology, and so on. And there were 25 features we call the biological tumor sample features. So these include like the sample weights, the number of fragments that were plated, the tumor digest count, and the number of the immune cells live in the digest. So there were also 10 possible targets in this data, but for the purpose of this talk and this study, we focus just on the overall TIL growth. So this is whether the patient, the tumor that were resected from them, whether they were able to grow TIL or not. Okay, so the machine learning protocol we'll be talking about is what we've called ML-PETIL. It's protocol for the expansion of tumor infiltrating lymphocytes. So we start with the data set, and then we split into training and testing. And then taking the training data, we perform feature selection. So we repeat this n number of times. I'm going to show you in a few slides how that works. But then the goal here is to identify what we call robust features. So when you identify these robust features, you go back to your data set. Now, working with those features, you generate a new split of your data into training and testing. And then on the training data set, you're going to learn the optimal support vector hyperparameters. So in a support vector hyperparameters, there are parameters that determine how wide your margin, the margin of the support vectors are, what type of decision boundary you're going to use, and so on, depending on the kernel you choose for the support vector machine. So we learn the optimal hyperparameters for the data, and then using those hyperparameters together with the training data and the test data, we generate support vector predictions. And then to see how well this prediction is, we use some accuracy metrics. Okay, so for the data we have, there are some challenges. So we can start with, there's incompleteness in our data. Several of the feature columns are actually missing data, so it's sparse with different level of sparsity. The feature columns, they are like of different data types. So which some of the features are categorical, which could be yes, no, and so on. And then some of them are real valued numbers. Some of them have high different magnitude of scaling. So this is an additional problem. And there's also imbalance in our data set, like I said earlier, in the study where they showed that 70% of the patients actually grow TILs. So we have more patients data that grow TILs than the no-till category. And then we're working with a very small data size. And also, as I will show you in a few slides, that there was also lack of diversity in some of the features in this data set. So looking at this challenge, we came up with like just 2 predictor data set. So the motivation is for the first predictor data set, we want the largest number of patients with a full feature set. So here we're able to select 37 patients, not missing data, out of 25 features. So these are features that were a combination of those 3 subcategories I mentioned. And then the motivation for the second predictor data set, we were interested in the immune cells in the tumor digest. We wanted to see how predictive those features were. And for those, we have very few patient data. So for us, we had 20 patients not missing data out of 10 features. And so that's our predictor data set. So here, I just want to show you from the data what these challenges look like. So incompleteness in our data, you can see in the sparsity in the feature columns. And then imbalanced data set, we had like 70% of the patient data grew TIL, and then lack of diversity, you can see that being very much visible in features like the sex or the race, but that's not true for all of the features like, and the demographic features like the age at surgery, that was pretty diverse. Okay. So here I want to talk about how we perform feature selection. So we actually use the random forest algorithm for feature selection, but just to show you what that looked like for our protocol. So if we take this sample instance of training data, we can create a subsample from this training data. So we start with that subsample, and then we build a decision tree. So from the decision tree, we're actually calling the classification and regression tree algorithm, which is going to be selecting a feature to start with, and it's also going to be choosing like a splitting threshold. And this is a greedy algorithm. It doesn't really matter whatever feature you start with. It's just going to start with one feature, set a splitting threshold, and then to kind of calculate the quality of the split, we can compute like criterions like the Gini score or entropy, depending on what you're interested in. And then you can use that at the end of the day to compute what is called the feature importance score. So when you build your decision tree, you can actually generate importance scores for each of the feature. So for a full random forest, you'll have to repeat this multiple times, and then you use like an ensemble learning method to aggregate all of these feature importance scores to then generate what you will be the feature importance scores for all the features in your training data. So to show you why you have to do that, why you cannot just use a few or just a couple of decision tree. So for instance, in this training data, if we just swap one of the patients, we see that the feature importance scores from the decision tree are highly variable, right? So we solve that problem by using random forest, and which is by using this ensemble learning method that aggregates all of those feature importance scores for all of the decision trees. Okay, so here's application of feature selection to our Predictor 1 data set. So this was the data set where we had 25 features, 37 patients, and which was a combination of demographic features, clinical, and the biological tumor sample features. So here we set a threshold that actually select the top 10 features in like 3 or 5 random seeds of this training data. So what that means is that initially when we split our training data into testing, training, and testing, we change the random seed and we repeat this 5 number of times, and then we select the top 10 in 3 of those 5 seeds. So having identified what we are calling now the robust features, the next thing is to choose optimal support vector hyperparameter. So I'm using this graphs to show you what that looked like in our protocol. So using the radial basis function kernel, which here, if we focus on 2 hyperparameters, where we can actually determine what type of margin we want to work with and what's the type of decision boundary we need. So we can actually train, we can learn the most optimal, and then we determine how good they are by using the classification accuracy, or also using the training and validation accuracy. All right, so when we generate this, so this is just showing you how well for the Predictor 1 data set and for Predictor 2 data set, where we had the immune cells in the tumor digest. So this is how well our predictor was performing. So we see that it performed well in the growth till category, and then not so well in the no-till category. So we can demonstrate that with this accuracy metrics. So we see in both predictor, we have good precision, good recall, and F1 scores. And those are metrics that actually show how well a predictive method does with the positive category. And so you can see with this specificity, which is a metric that shows how well we should be doing with the negative category, in this case, the no-till category, we see that in one of the predictor where it's our model is just guessing, and in the other case, it's not doing anything at all. And so those are some of the challenges, like I said, in this data set, which we had more data for the growth tills and very few data in the no-till category. Okay, so in conclusion, what I've shown you, like we've developed this protocol, ML-PETIL, and we can use it actually to predict expansion of tumor infiltrating lymphocytes. We've demonstrated that we can identify robust features, and the goal is to stratify patient eligibility for the immune-based therapy I mentioned. And then we've also shown that we can optimize these hyperparameters for some metric scores like the F1 score to be in the near 90%. But we have some challenges still to work with, which is our next step. Like we want to compare different machine learning techniques to handle missing data and to also handle imbalance in our data set. And also we want to include in our protocol an optimization for the way we select our thresholds in the feature selection portion. And just to say, we will have access to more patient data. It's in the process of de-identification at Murphy. And also the clinical trial that just opened in a period of 3 years, we're going to have additional 12 patients to work with. that's it. Our acknowledgement. I'm grateful to my mentor, Dr. Kasia Regnak, other members of the lab, former member of the lab, and our collaborators, and also acknowledge our funding sources, and also to say in our lab, we're recruiting for postdocs. So that's it. Thank you.
Hi. It seems that the biggest trouble you have here is in your patient feature matrix with the gaps, imbalances, and stuff. It seems my first question is answered with your future steps. The question was whether you tried imputation. So I guess
yes,
you did.
No, we tried some not good results yet, but presently we're working on using like generative models, like the, variation autoencoders, so whether we can do in an unsupervised way, and then to do imputation, and then to compare with different imputation techniques. So we are working on that. Yeah.
Okay, I had a different second question, but at the same bullet point about future directions, you spoke about the imbalance of that same matrix. What did you mean there? The imbalance?
Also, we're just saying, mostly for predictive methods, it's always nice to have like near 50 or almost the same ratio for the different classes in your target. But for us, we had more growth tills than no tills. So that's the imbalance in our data set.
Okay, and you used that random forest for feature selection. To me, it's a horrible black box. Did you try something as simple as GLM, for example, as at least step 0 in your feature selection?
Say that again. Did you try?
Generalized linear model.
Oh, okay.
As a step 0, this seems to be the simplest approach that could give you right away what falls out. You could, even a simpler one would be to look at the distributions, and where you have the smallest sigma, you try to throw that out, but that would be too crude, I guess. So you could do something less fancy, but more kind of hands-on.
Okay. Yeah, okay. Yeah, thank you.